Welcome back to Introduction to C++. My name is Kate Gregory, and I'm introducing you to the most popular general-purpose programming language, C++. In this module, I'll talk about polymorphism in C++. Now, polymorphism doesn't sneak up on you. It can only happen when you have classes that inherit from other classes and pointers. It's actually an incredibly useful and productive technique. When you get to talk about polymorphism and pointers to objects and base classes and derived classes, you have other pieces of vocabulary like virtual, slicing, casting. You know, to really get the C++ pointers story, you need to explore what happens with pointers to objects that are part of an inheritance hierarchy. So let's do that. Pointers are straightforward when the objects that you have a pointer to are just flat objects with no base class. So far you've seen pointers to integers, to person, to resource. When you have an inheritance hierarchy, then you have to understand the rules around pointers to a base class and pointers to a derived class. When you do an object-oriented design, you often use the test sentence ISA. So imagine a hierarchy where I have a base class bank account and some derived classes checking account and saving account. It's about a 30-year-old example, but it's a goodie. A checking account is a bank account. A savings account is a bank account. And if some function takes a bank account pointer, you can pass down a savings account pointer or a checking account pointer, and that function shouldn't complain in any way. It's a Liskov substitutability. In C++, it's done with pointers. The function takes a bank account pointer. I give it a checking account pointer. It thinks of it as a bank account pointer, stores it in that base class pointer, and then obviously calls only base class functions using the pointer. I haven't designed bank account, I just started talking about it, but imagine it's got get balance. That's a function in the base class. It will be in the derived classes. Both checking account and saving account will have a get balance, and so this code that expects a bank account pointer can go ahead and call get balance in total confidence. It's guaranteed to work. But a question arises, what code will run? In a lot of languages, you may think you know the answer. Oh, it's the more derived implementation in the subclass. In C++, it's up to the programmer. You decide when you write bank account whether get balance is virtual or not. If it's virtual, then the derived class version of the function will run. So saving account, get balance, or checking account, get balance. But if the author of bank account made get balance non-virtual, which is the default because it's the fastest, then only the bank account version will be executed, even when the object in question is really a savings account or really a checking account. You as the developer get to choose whether you want virtual functions or non-virtual functions. In C++, virtual functions are implemented through a virtual table, which is a little collection of memory that has the name of the function and where to find the code for it. You don't really care, and in fact the standard doesn't insist on it working this way, but the point is at runtime there's a little bit of a cost of figuring out what function to run. And your program is a little bit bigger because of the memory taken up by the virtual table. If your class has no virtual functions at all, it will be a little bit smaller and run a little faster. And in some cases, people want that. So you get to choose virtual or not virtual. Now, this relationship base and derived only works in one direction. So you can't take a bank account pointer and hand it to something that's expecting a checking account pointer. That's not fair. Checking accounts might have, I don't know, overdraft limit, and your bank account doesn't have that. So a pointer to an actual bank account can only be given to code that's expecting an actual bank account, not to something expecting a checking account. But a pointer to a checking account can always be given to code expecting a bank account because a checking account is a bank account. Interestingly, when you use smart pointers like shared pointer and unique pointer, you can get this same polymorphism preserved, exactly the same behavior as if you were using raw pointers. Since I consider using smart pointers to be a best practice, I want to make sure that you know you're not giving anything up when you use them in an inheritance hierarchy. Tweeter hierarchy throughout this material. Let's use it again. Here I have a very simple console app that's going to create some pointers to person objects and tweeter objects, and it's going to make a bunch of method calls on those pointers. There are a lot of different versions of person kicking around depending on what I want to demonstrate. Let me just quickly show you the header file for person. It just has first name, last name, arbitrary number, doesn't really have any operator overloads or anything much going on, and has some get and set functions here: get name, get number, and set first name. And these are just easy functions for me to call and see what happens within the class. Tweeter inherits from person and has this overload of getName. Any two functions with the same name we call overloading, even if they're in entirely different and unrelated classes. So we have operator overloads, and this is certainly an overload. We have getName here in person and in Tweeter, and there's been a number of objects and classes showing up over time in demos with getName functions in them. But getName, in addition to being an overload, is also an override. I want the tweeter getName to be somehow different from the person getName. So let's be reminded of what the person's getName does. It just returns the first name, and then a space, and then the last name. And in here we have an attempt at writing a tweeter getName. We'll go with the first name, the last name, and the Twitter handle. But you notice there are red wiggles. If I hover over them, they say, error, person last name, blah, 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 is inaccessible. And the same for person, first name, inaccessible. Let's go back to person. Right, they're private. Private member variables are not accessible by any code outside the class. I have a couple of options for how to make this right. One would be to add individual get first name and get last name public functions to person for no other reason than to let Tweeter call them. That's a bad idea. I see people do it a lot, but it's a bad idea. Another would be to change this private to protected. Protected is a language keyword that says it's private unless the code is in a class that inherits from this class, then it can do what it likes and party on the data. I consider protected to be a to-do list. Right now, getName returns first name, space, last name. But if you have a business requirement to suddenly change that to last name, comma, space, first name, if these variables are protected, you're going to have to go looking for getName elsewhere in classes that inherit from person. And depending on your platform architecture, it may be a challenge to find all the classes that inherit from person and change them to print out first names and last names the new approved way. My preference, leave this private and use this perfectly good getName function that's already been written. That way, if anyone ever changes getName in the base class, we'll get the changed behavior in the derived class. Much smarter. So I'll just go back into tweeter.cpp, take these, and what I want is to call person's getName. Where am I going to get a person object to use the dot syntax on? Some p dot getName. Well, I don't have one. But I can still call it from in here by using its full name. Return person getName. Now I'm in a position where if someone makes a change in the base class, I'll just naturally get that change in the derived class. I don't have to worry about private and protected anymore. I'm not trying to talk to private variables. This is all good. That makes my project compile, but that wasn't really what we came here for, right? We really came here to see what happens if I talk to some objects using different kinds of pointers. So let's go back and look at this main. I'm creating a person on the free store, and by the way, forgetting to delete it. It's a deliberate memory leak here. I'm creating a tweeter also on the free store, which I do remember to delete. And I'm creating a person pointer that's equal to this tweeter pointer. So just two ways of looking at the same piece of memory out on the free store. And then I'm going to call getName on the Kate pointer that I got from newing up a person, on the Kate GregCons pointer, which is a tweeter pointer that I got from newing up a tweeter, and on the pKate GregCons, which is a person pointer that came from newing up a tweeter. Remember that the person getName just prints their name, the tweeter getName prints their handle as well. So let's run this. And here's what happens. When I use the person pointer, which is pointing to a real person object, not surprisingly, I get person output. When I use the tweeter pointer, which is pointing to a real tweeter object, not surprisingly, I get tweeter output. When I use a person pointer, which is really pointing to a tweeter, I get person output. Some of you might have expected differently, but getName in person.h is not virtual. And because it's not virtual, I will always get person output. If I want to see a tweeter code for getName run, even when I'm using a person pointer, as long as it's really a tweeter object that the person pointer is pointing to, I need to make getName virtual. Now I only need to do this here in the base class. I don't need to do it in tweeter. You can if you want as a form of documentation, and I don't need to do it throughout all of the inheritance hierarchy. I can just make this single change here and then just run it. And you see now the tweeter code ran even though we were using a person pointer, because it really points to a tweeter object. And when the function's virtual, that's what drives it. Once I have a virtual function in person, I will have a virtual table, and I will take that small performance hit. At that point, a rule kicks in. Now, it's not a compiler rule. I don't have any warnings from the compiler. This is a best practices rule. I want you to kind of go on a thought experiment with me. Imagine that I knew this tweeter up, and I don't call delete using the tweeter pointer, but instead I call delete using the person pointer that points to the same place. The destructor for person and tweeter is currently non-virtual. Here's the destructor. This destructor actually doesn't do anything. We'd be better off taking it away, but bear with me. We have this destructor. It's not virtual. If instead of deleting the tweeter pointer, we call delete on the person pointer, you know what would happen? The person destructor would run. So what? Well, it depends on the class. If tweeter manages something, like it opens a file and its destructor needs to close the file, and I delete a tweeter object using a person pointer, I still want to run the tweeter destructor. I still want to close the file or release the lock or let go of the database connection or whatever my destructor is going to do. How can I prevent this leak where we call the wrong destructor? How can I be sure that if the object being deleted is really a tweeter object, that the tweeter destructor runs? By having the destructor be virtual. Now, some people go so far as to say that all destructors should be virtual. I don't agree with that. That just makes the overhead of virtual functions come into every class whether they're needed or not. But a really good rule is the minute you have one virtual function, clearly you're expecting to be using pointers in an inheritance hierarchy and for virtuality to matter. There's a really good chance that somebody might call delete on a person pointer that was really pointing to a tweeter object. And despite the fact that as the person author, I have no idea what might get added to tweeter, don't make the destructor virtual before there are any other virtual functions, but the minute there's one virtual function, get in there and make the destructor virtual. It will save you from a really subtle bug that is extraordinarily hard to track down if you don't just happen to recognize this pattern and this best practice. Let's change this demo from using raw pointers, person star and tweeter star, to using shared pointers. I'll include memory. That brings me in the shared pointer. And since I already have using namespace standard, I can just call it shared pointer. So let's make a shared pointer of person. We can call it shared pointer to Kate. And there's a couple different ways. We used make shared in other demos because we weren't declaring and initializing the pointer at the same time. Here, I can, if I wish, simply new up a person and put it in here. Or I can use equals make shared at person. And again, pass in those arguments. I'm just going to steal these arguments. And I'll put an S and a P. We're not going to be very pronounceable, but we'll be able to tell our objects apart. This line of code compiles. I'll build it to prove it to you. But it's a little repetitive. Why do I have to say the type here and here? Interestingly, make shared of person returns a shared pointer of person. And in C++11, we have this cool capability, which is I don't have to type out the type of an object if the compiler knows what it is. So here, I can actually use this C++11 keyword auto. When I do that, if I hover over SPKate, you'll see it's a shared pointer of person. It has a type. I just didn't have to come up with it. Its type is whatever make shared returns. I can, of course, interact with this pointer the same way we did with the raw ones. So I could take this line, paste it here, and all I need to do is change the variable to SPKate, and that's just fine. I'm dereferencing the shared pointer to call its getName function. I could also go back to calling this a shared pointer to person, but create it not by calling make shared of person, but by calling make shared of tweeter. So this will now be a shared pointer to person that's actually pointing to an object that was allocated out on the free store as a tweeter. I'm going to need another parameter to my constructor for a Twitter handle. And if I run this, you can see I got the tweeter version of getName. In other words, our shared pointers are being appropriately polymorphic. A shared pointer of person that really points at a person, you get the person code. No surprise there. A shared pointer of person that really points at a tweeter, you get the tweeter code because it's a virtual function. It just works exactly like a raw pointer.